Okay, so welcome back to another video. So here today we have a improper integral integrating between from 1 to infinity of the fractional of x subtract 1/2 divided by x and then dx. So you're probably thinking to yourself, what is this little function over here? What are these brackets? Well, this is actually known as the fractional part of x, and that's the formula is defined for this is set to equal for x subtract with the floor of x. And so this works for x is a positive real number. Now, what if we were to have a negative number, for example? Well, the only thing that really changes is just that instead of the floor of x, it'd be the ceiling of x, which acts as the least integer function, just as the floor function acts as the greatest integer function. So if we just use this definition of the fractional of x, plug this back in with the substitution over here, that's basically step 1. We can see that also by utilizing the definition of the floor function where it acts as between, again, it's known as the greatest integer function. So what we have to do in this sort of situation is we want to break up into a sum of integrals going from 1 and all the way up to infinity. So and integrating each term wise. As you know, in between, like integers, it only accepts integers only, but we're dealing with positive real numbers. It has to act in between each of the integrals as we take those sums up. But the integration part's the easy part, but what it really comes down to is evaluating the entire sum to get to that finite value, which there's going to be a lot going on, which is going to be a very exciting deal. Don't want to give too much of what's going to happen. I just gave you just a little bit of what to, expect for the premise. So why don't we actually just jump right in. So if we do this substitution, so I'll put back the fractional of x back in, so with x subtract the floor of x. So we have our new integral, so that would be x subtract the floor of x, then subtract 1/2. All this divided by x, and then dx. So we need to do something about the floor of x. Well, by using that definition of floor of x, so we can say that the floor of x is equal to k, where x is actually in between the half open intervals, so it's closed inclusive for k, and then all the way up to k plus 1 non-inclusive, where where k is an integer. Just from using that, now we can actually do the substitution, but by doing so, we would actually have to break up this sum of integrals as we do is like one step at a time, since it's only dealing with integers at a time. Okay, then right, so we actually can get this infinite sum. I think it's also worth noting that I should call this integral I, just so we don't get any sort of mix-ups. So this is infinity. Then we say that we can start from k is equal to 1. Our integral starting from k to k plus 1 of x subtract k minus 1/2, and then divide by x and then dx. Okay, now evaluating this definite integral, that's actually a piece of cake, because what you'll notice is that now we actually have to I already said that already. If you want to actually check to evaluate this integral just for verification, I'm actually just going to skip that step. What it comes down to is that we still have our infinite sum. So now what it is that now we have that this is 1 subtract k plus 1/2 multiplied by ln of k plus 1. Add this with k plus 1/2, then multiply with ln of k. And so again, now we just have to evaluate this infinite sum. To make things a little bit easier, we can write this as a limit, and so really it makes it easier for the stipulation such that we need to figure out how to evaluate the partial sum itself. So with that, so everything I'm just gonna write the same thing, so just give me 1 second. And so now what we can do is simply just applying with the continuity, I can actually just distribute each of for the partial sums into these terms over here. So of course we still have our limit to evaluate, so that's no surprise. So now we have the partial sum k is equal to 1 of 1. Then we add this, or rather subtract, with the partial sum of k plus 1/2 multiplied by ln of k plus 1. Then just add this with the partial sum k is equal 1 of k plus 1/2 and then ln of k. Now, there's several notes that I want to make before we, continue on forward with evaluating. So we're actually going to take this one step at a time. Let me first put this in green, or actually blue's better. So one thing we want to observe is specifically for this term over here. This may be difficult to evaluate this from further, but that's why we're making these observations and doing a little bit of, algebraic manipulation. So note that specifically, okay, so let me put this note first, then I'll write our partial sum we want to pay attention to, k is equal 1 of k plus 1/2, then ln of k. What we can do specifically is the inside expression k plus 1/2. Again, we can perform some arithmetic changes. We can write that as k minus 1/2, and then add this with 1 and multiply by ln of k. All right. Then if we actually just do some of distributive properties, so just put the ln of k with k minus 1/2 and then put this with 1. So now we actually have our new sum, well, rewritten, and put it better for worse, k minus 1/2, then ln of k, then I can add this with the partial sum, k is equal 1 of ln of k. All right. So now from here, I can actually just substitute this back over here. So let me see, I'll put this right there, right, just find the way it is. Okay, so now by doing so, now we have our new sum. So let me actually, stick with this is fine. So I need to have that I is equal to, so we have the, so we still have our limit and approaches infinity. Okay, and then basically I'm just rewriting the same thing. So n, k is equal 1 of 1. This is still going to be the k equals 1 of k plus 1/2 multiplied by ln of k plus 1. Okay, and I'm just going to move on to the next line. So now we have, now add this with our substitution over here. So n, k equals 1 of k subtract 1/2 ln of k, then add this with the partial sum k is equal 1 of ln of k. All right. And so now what I can do here is we can actually do a little bit of regrouping. So applying the continuity, I can actually put these two terms together as under one partial sum. So first, let me just get to that step. So now right here we have a minus and a minus. So I'll just, just factor that out. So let's see, we have n, k is equal 1, k plus 1, well, 1/2, excuse me, multiplied with ln of k plus 1. All right, and then now this is going to be, we just factor out the subtraction, so now this will be a minus k minus 1/2, then ln of k, and then now we just put back the ln of k over here. With this, so maybe make things a little bit easier for us, but now let's also make a couple more observations and notes that we want to pay attention to. So now let me actually switch to this color now. So here, our first note we want to obviously observe is that specifically this partial sum over here. Since it's just 1 and you're doing this for n times, so basically the partial sum of 1 is actually just n. So let's let me put that down first. K is 1 is equal to n. Okay. And then another one we want to observe is specifically the ln of k, the partial sum of ln of k. You'll notice that n, k is equal 1, ln of k. What you'll notice is that since if you were to expand this out by using natural log properties, we can actually apply that continuity and say that this is just a natural log of the product series from k is equal 1 to n of n. But simply, that's actually, that input argument is just basically the definition of a factorial. That's actually supposed to be a k over here, not an n. So really, when expanding this out, so really we have the natural log of n factorial. Okay, so that's nice. And there's actually one more adjustment that we want to pay attention to, and that's specifically the middle term over here. So I know I split this into two lines, but I'm just trying to save room. So it's this sum right over here. Okay, so let me put that down. And k is equal 1. So this means what we're looking at is k plus 1/2, then ln of k plus 1, subtract with k plus 1/2, and then multiply by ln of k. So here's something to observe over here. So if we were to do the series expansion, so we plug 1 over here, so obviously ln 1 is going to be 0, so that just vanishes. Over here, plug 1, so that's 3 over 2, and then ln of 2, so, or 3 over 2 times ln of 2. You plug in 2, so this would be 5 over 2, then ln of 3. Over back here is 3 over 2, then ln of 2. If you just keep going so on and so forth, you'll notice that this is actually, the terms actually cancel each other out, and so this means by definition that's a telescoping series, meaning that what you're really left from that expansion is your first and your last term. But from the first term, we said that if we put k equals 1 over here, we have an ln of 1, which is equal to 0, so that's completely out of the way. What really matters is that what's left is the final term, you just plug n. So everything from the right side, when you group these together, actually disappears. So we're actually left with this, so you just plug n. So now, really, the expansion actually just comes down to n plus 1/2, and then ln of n plus 1. And so now, just from this, now we can actually just keep going and apply, well, not apply, but perform our substitution. So now if I just go back, let's see, I plug this back here, so so far, if we do our substitution, n approaches infinity. So now, the new substitution after everything we just observed, so now we would have n, and then subtract this with n plus 1/2, multiplied by ln of n plus 1, and then just add this with ln of n factorial, just like that. There's still some discrepancy on how to evaluate this even further, but I think the bigger issue is trying to figure out how to evaluate the middle term. No worries, because what we're going to do here is we're actually going to consider a limit, so a difference of limits, really. Why do we do this? Well, you'll see what happens as we proceed forward with this. So let's consider a limit L, okay? So we say that the limit as n approaches infinity. I'll put this as, first we have n plus 1/2, and then ln of n plus 1. Then what I want to do is I want to subtract that with this limit. So this is still n plus 1/2. And then instead of n plus 1 as the input, this is actually going to be multiplied with ln of n. So now, just doing some algebraic manipulation, what I can do is I'll just factor out the n plus 1/2 from both sides. And there's both limits that tend towards infinity, so it's, you know, just using that continuity right there, it's fine. Let's see, so what I say, so the limit n approaches infinity, this is n plus 1/2. Then I say ln of n plus 1, then subtract ln of n. But again, you can actually apply natural log rules, so this is still the same thing. But now we have the natural log of n plus 1 divided by n. Now to make things a little bit easier, let's actually just do more distributing. So distribute the n plus 1/2 into that natural log. So the limit n approaches infinity. So now what we have is we're going to have still, again, difference of natural log, or rather sums of natural logs since there's a plus. So this is n, then multiplied by ln of n plus 1 divided by n, and then add this, 1/2 is a constant, so I'll just move that outside of our limit, so 1/2 times the limit, n approaches infinity, of ln of n plus 1 divided by n. So you'll notice that we have a much easier limit to evaluate, and what's the easier part specifically? Well, it's this one over here. Natural log of n plus 1 divided by n. In other words, you can write the input as 1 plus 1 over n. Take that as it approaches infinity. Obviously, 1 over n, as n towards infinity, is actually going to approach 0. So 1 plus 0, then natural log of 1 is 0, and so therefore this limit right here is actually just going to equal 0. And so what we have left now is we need to evaluate this limit over here, which might give some bit of a situation that puts us at a hole, but that's actually not an issue, because what we can do is, if you notice that we have n approaches infinity, if you were to do this, you can't really get much out of it, because you have, again, so ln of n plus 1 over n, we just said that that's ln of 1 plus 1 over n. Take that as it tends to infinity to 0, but you have a infinity times 0, doesn't get that much of impression on how we're supposed to proceed forward, but that's okay. We can actually apply L'Hopital's rule to do this, but we can't, because well, I'm saying we can apply L'Hopital's rule, but it looks like we can't, but we actually can, because we can actually rewrite this as a form of like a rational function. Specifically, the n can be moved to the denominator, and that will be written as 1 over n. So we have the limit as n approaches infinity. So this will be ln of n plus 1 divided by n, and then divided by 1 over n. Okay, so what we see here is we take this as n approaches infinity. You actually get a 0 over 0 indeterminate form. So indeterminate, I'll just abbreviate that. Okay, so now all we have to do is actually just take the derivative of both the numerator and the denominator. So we have the limit as n approaches infinity. So let's see, we have 1 over n plus 1 divided by n. Just flip the reciprocal, so this is just n divided by n plus 1. Multiplied by the derivative of the inside, so the derivative of 1 plus 1 over n. So let's see, derivative of 1 is 0, and the derivative of 1 over n is just negative 1 divided by n squared. And so that's the same thing for the denominator as well, so negative 1 divided by n squared. Okay, but easily, as you can tell, these two just cancel each other out. And so now we just have to evaluate the limit n approaches infinity of n divided by n plus 1. But you'll notice that if you take a look at this, they both share the same degree from both the top and bottom, and when you're taking the limit as it approaches infinity, it's just equal to just 1. And so therefore, that's our limit right here. Let me actually just underline this. So this is equal to this. But you might be thinking to yourself, but L is equal to 1, but how are we supposed to evaluate this following limit? Well, simply, all you have to do is just subtract, so going back here, so L is equal to, so really I'll just write the final answer of what we want to evaluate. So we have that 1 is equal to this limit, subtract this limit, but what we want to evaluate is this limit over here, but all you gotta do is just add this to the other side. So now we just have that the limit as n approaches infinity of n plus 1/2 times ln of n plus 1 is simply just equal to 1 plus the limit as n approaches infinity of n plus 1/2 and then multiplied by ln of n. Okay, easier said than done. So now let's actually perform a little bit more substitutions. Okay, so going back to over here, we have that I. Okay, so what I can do here is we have that I is equal to the limit as n approaches infinity. So now we have a n, then minus, so I'll just put this, because there's nothing be taking the limit up for 1, so I'll just move that outside of our limit, but we just have to put this back into here. So this is actually going to subtract n plus 1/2, then ln of n, add this with the natural log of n factorial, and then subtract 1. But now you might be thinking, how can we proceed forward with this? Well, what we can do is, everything has natural logs in here. Natural log here, natural log there, but except this. But no worries, because we can write that as, so note that n can actually equal the natural log of e to the power n, so I'll just substitute that back in. So now this implies that, let me actually back up just a little bit with the camera so it takes up a little more space. So now just from applying here, so we actually just apply our natural log rules. So we're going to have that this is the limit as n approaches infinity of the natural log of, so this will be e to the n, then we just move that to the exponent. This is minus, so that's going to go in denominator, and then this is a plus, so that's on the top. So then this will be times n factorial. Divide this by n to the power n times the square root of n. This is still subtract 1. Now you might be thinking that this is probably where it ends, right? Like we don't see how we can simplify this even further. Well, we technically can. I did use this formula before in the past. We're actually going to be using that to do that substitution, and that is known as Stirling's formula. And Stirling's formula says that this is actually an approximation of factorials, and factorial is asymptotic to the square root of 2 pi n, and then multiplied by n divided by e, then to the power n. Okay, so just from that we can actually do that substitution. So now we have the limit as n approaches infinity of the natural log of. So if I just put this back in, e to the n, then now we have n to the power n, that's just coming from over here, multiply the square root of 2 pi n, all this being divided by, so e to the n over here, and n to the power n, and then square root of 2, or square root of n, then subtract 1. you'll notice that we have some terms that cancel each other out, and notice that we have a radical under a radical, so we can combine that together. So that cancels, cancels, cancels. This is actually just the square root of 2 pi n divided by n, then the n's cancel, and we're actually just done. We're actually done here, so that means our limit I, well, because there's nothing to take in the limit in terms of n because the n's cancel each other out, so we're pretty much just done. We just have a constant. So therefore, our final answer is that I, which is this integral over here, is equal to the square root of 2 pi. Or if you want to put this, you can say this is 1/2 times 1/2 times ln of 2 pi, then subtract 1. And so there we have it, the final answer in the blue box, just like that. Yeah, so I think this is actually really cool, you know, integral to evaluate, especially with the fractional part. It made me realize that I did actually cover a fractional integral in the past, but it was actually the fractional of tangent of x. So if you haven't seen that, I'll leave that link in the description below for you to check. I think that was probably the first fractional, well, probably just something fractional part related that I covered in the video. I could be wrong, but you know, I'll let you guys know. So there we have it. Just from starting from what we have, using that definition of floor function, create this into you know, a definite integrals and a sum of integrals, evaluating this sum, so everything we have here with taking terms of limits, and so there we have it. So yeah, that's pretty cool if you ask me.